The first speaker is Dr. Tom DeSutter with NDSU, North Dakota. And I bring in Dr. DeSutter because he's one of the best I know when it comes to sodic soils. And he honestly, I've listened to his classes, his lectures, his talks, is one of the most enjoyable personalities. And he's also a great ice fisherman and has taken me along. But with that, I want to let Tom introduce himself, share his screen, and get into his talk. Remember, we're going to have 25-minute talks. After each talk, we'll have a couple minutes, but at the end of the session, we'll have opportunity for roundtable. And at the end of the last speaker, Dr. Gilling, I'll put up the QR code for the CCAs. Dr. DeSutter, floor is yours.
All right, well, thank you. Are you able to see that, Brian?
Yes.
Okay, thank you. All right, welcome everyone to, well, it's cool North Dakota, but it's probably a little bit warmer down south. So today we're going to talk a little bit about managing saline and sodic soils. So I spent a bit of my time for my PhD at K-State doing inorganic soil chemistry, came up to North Dakota, and it just so happens that everything to do with saline and sodic soils is inorganic soil chemistry. So my passion has remained strong for this field, and North Dakota in itself, in the northern Great Plains, we do deal a lot with these problem soils. So it's a good, I thank Dr. Arnal for inviting me to speak with you today. So we'll go ahead and get started. So even though we have lots of salt, Australia basically lives with it in many ways. And for a long time, they had this magazine called Salt. And so this is one of my favorite quotes of this whole thing. If you've got salt, learn to live with it. And there's a lot of truth to that because it's one of the harder things to manage from a crop production standpoint. So a little bit of background on what is saline versus sodic. So saline soils basically contain elevated levels of the chloride and sulfate salts of sodium, calcium, magnesium, and potassium. So when we say salts, we're talking about the crystalline form, but when you add that crystalline form to water, you get the ions, sodium, calcium, magnesium, potassium, sulfate, and chloride. So we tend to use those very interchangeably because of the fact that saying salt is easier than saying ions and cations and anions. So anyway, so basically it's the total concentration of dissolved mineral solutes that are found in waters and soils. And at elevated levels, they can negatively affect plant growth. Where sodic soils tend to not to be as common, but these are the ones that are affected by basically the sodium ion. And we often say that these are sodic, these soils are sodic. If we're looking more on the soil taxonomy side, we would say that they're natric. And so, but these soils oftentimes have low salinity, which is what drives their properties. When they dry, though, they become hard set, they can crust, they restrict root penetration. But when they're wet, this is kind of a weird thing about them, is that there's really no bottom to them. And you get them at the right water content, man, and you can get stuck very, very quickly. So are all salts and sodium bad for soils? I think that's a fair question. And of course, from a soil science standpoint, you always say, well, it depends. And so all of our salts, all of our soils have some level of soluble salts, okay, even our most productive ones. Those are oftentimes are what our plants are taking up as soil fertility. But not all salts will hinder soil structure. And the sodium sulfate, sodium carbonate, sodium chloride, those can eventually hinder soil structure. But when you have flocculating cations, such as calcium, you can actually, the soil particles, the clay tectoids will hold together much better, especially if the electrical conductivity is managed. Okay. But in my part of the country, we have a lot of soils with high concentrations of carbonates, lime. And these soils tend to be fairly friable, and therefore they are very susceptible to wind erosion. Now, these aren't the same sort of carbonates, caliche type things that, you know, a lot of you will deal with in the South, but the calcium carbonate just doesn't do well enough after it's been tilled, and things will tend to get very fluffy, and when they get fluffy with a lot of wind, well, I think you folks know what can happen then. So, well, here's a couple of pictures that are sort of quote unquote fun to look at. So in the upper left-hand corner, you have an aerial photo from the spring of 2014. This is in southeast North Dakota. You can notice that it just got done snowing. Well, wait a minute, let's relook at that. Well, if you look at the other one, it still looks like it's snowing. But if you zoom in a little bit further, you notice that these are all salts. So in the southeast part of our state, this is a common look, especially after spring snowmelt. But it's not just common to southeast North Dakota. You can drive across many of the highways and roads in the eastern part of North Dakota and see this very similar, unfortunately. Okay, as far as sodic soils go, these have a much different structure to them. So basically what has happened is that you have clay or you have sodium, it has dispersed the clay and the organic matter. The organic matter then migrate down and they end up forming these columnar structures. And so this one was actually in southeast North Dakota. This one was way in the western part of North Dakota. But they can get very, very hard. And you can about imagine. So if you look closely at, you know, these, you can see those roots trying to follow down along those pathways, trying to get through those very hard set, high clay concentration. And oftentimes you'll see with these, you'll have the columnar structure, but then you'll have what's called the E horizon on the top of it. And basically, in many cases, it's all just dust for the most part. So both saline and sodic soils can be very scattered on a landscape. Here you have, this is an area of high sodicity. These are areas of high sodicity. So it becomes very difficult to manage from a grower's standpoint because of the fact that you have this scatteredness of soil properties across. You know, if it was an irrigated system that had a uniform application of poor water, well, then it's a lot easier to manage. These end up being a bunch of nuisance spots for the farmer because of the fact that as they're doing their field work and they're moving across, they can get stuck in this, but as soon as they get out of it, they're fine. And so they become more of an irritant over time. And again, they become very patchy. Here, this area where the shorter grass is highly sodic, and here it's not. Okay, just a change in elevation of 1 inch over 9,000 years makes a huge difference in soil development. But when you start tilling everything, you know, back in the day, we did a lot of tillage. It mixed up all the sodic properties with the subsoil properties. And so you don't get that neat textbook columnar structure that you might expect to see. Okay, well, we try to battle it a lot, but I know in Oklahoma, it's cherished. So you have your Salt Plains State Park, where it's encouraged for people to go and dig into it and things of that nature. So I spent a lot of time in Kansas when I was a technician and when I was doing my PhD, and I'm very disappointed that I never got a chance to go down and see this. So I'll have to go down there here after things clear up and go walk around in some more salt flats, or I could just do it in North Dakota. So where do we expect to see a lot of the saline and sodic soils occur? Well, look at this blue line. That is basically the line where precipitation equals potential evapotranspiration. So when we're talking about managing salts, it's all about managing water. If you can manage, or if you understand how water moves in soil, you can start to understand how to manage soil salinity. So I don't know what the red line is right now, but watch the blue line. And then we're going to look at the sodic soils across the United States. So here it is. Well, what do you notice? Well, most of the sodic soils in the United States are on the west side of that line. And why is that? It's because there's not enough water to move the ions through the soil. Now, I don't have a map of the sodium affected soils, but Joe Brennan, who's with the St. Paul office, made this for me. But in Oklahoma, you have a few spots, and I guarantee you that area where that salt park is. Here you have a plateau area up here where there's a fair number of sodic soils. And for example, up in that area, you have a Pawhuska series. And if you look at the taxonomy and you spend a little bit of time with understanding how the taxonomy is structured, you'll oftentimes see that there'll be a NATRA abbreviation in there. And that's basically designating that it's a natric soil that has a high concentration of sodium in it. Okay, so you'll have it was up in that a Red Prairies region. And if you look at the BTN, if we go down that A horizon, the BTN horizon, and so on and so forth, you'll notice that there are a few grayish coatings on tops of columns, effervescent, slightly alkaline, meaning that there's not a lot of salts for example, in this natric soil. If in fact there were salts, higher electrical conductivity, this end part, which describes it being natric, would no longer be there. Okay, because the soluble salts are what control the ability of that sodic soil to either swell, disperse, or flocculate. So which salts will likely move faster in soils? So when we always talk about, like, if you can manage the water, you can manage the salts. Well, the movement of the salts will depend on the water flow in soils, okay? Where if you have saturated flow versus unsaturated flow. And because of the fact that the solubility, whether it's highly soluble in soil or whether it's lowly or very not very soluble, will dictate how fast it moves into that system. So let's look at a couple of common salts that we have in our soil profiles. Okay, we talk about lime all the time, right? So this is calcium carbonate, but it has a really, really low solubility. So basically, if you would take Lincoln's face off of a US penny, and put it in a liter of water or two of your water bottles, that would be about the mass that would dissolve in there. Okay, so let's go to calcium sulfate, for example. So this is gypsum, right? We talk about gypsum all the time. This is about the mass of a US penny in a liter of water. Okay, so let's go to sodium chloride, regular old table salt. Now, if you have brine spills, you have shale oil, and when the oil comes up, it's an emulsion of brine, old ocean water, and the oil. Normally, oftentimes it's sodium chloride, but look at the solubility. I mean, that's like 130 US pennies in a liter of water. So the solubility makes a big difference. So if you think about which one's going to move faster in the soil, well, the one with the most solubility. And, magnesium chloride, magnesium sulfate. In North Dakota, we have a lot of magnesium sulfate. We have a lot of sodium sulfate in our systems. So very highly soluble salts. So they move up and down the soil profile very easily. So in general, though, chloride salts are more soluble than sulfate salts, which are more soluble than the carbonate salts. So the chloride and sulfate salts will move with the water much more readily than will the carbonate. Okay, so why do we even care about this? Well, ions have an affinity for water molecules. So when they dissolve, they want to be hydrated. And when they hydrated, that water then is no longer available for plant use. So the more salts that you have dissolved in the soil solution, the more of those, the water is going to have an affinity for those and hydrate them. And therefore that water will not be available. So it takes plants a lot more energy to extract that from soil, extract that water from soil. So that's why when you see plants that are in high saline soils, they kind of look really droughty. Well, it's because of the fact that they can't utilize the water that's there. But the depletion of water through evaporation, drainage, or plant uptake further lowers the osmotic potential. So, we talked about our old soil physics. You have gravitational potential, you have matrix potential, and osmotic potential. Well, this is the osmotic potential. It's not dictating where the water moves, but it's dictating how the water is able to cross a semi-permeable membrane. Okay, so if you're going to manage saline soils, usually the first thing you do is you think about crop selection. And as you know, crops have variable sensitivities to salinity. So on the bottom, the x-axis, we have the saturated paste electrical conductivity. And here we have relative crop yield, where if you don't have any issues, you have 100% of crop yield. So let's just take maize, for example, or corn. If you have a soil EC of 5, you can expect to have about a 65% relative crop yield, as an example. So I do want to shout out, though, that James Moss is actually from North Dakota. So if you ever see these old figures, he was with the U.S. Salinity Research Lab in Riverside. So choosing the right crop for the situation you have is one of the most important things. Now, so we do have a video that was produced by the NRCS, in conjunction with our North Dakota group. And one of the quotes in this movie, it's about 24 minutes long, but it's really informative. And I think if you have a lot of salt issues, it'd be worth the time to watch it. But one of the guys in there says, if you're going to manage salts, you got to grow your way out of it. And that's a very true statement, because it's hard to manage the water without a lot of dollars. But you can change your cropping practices to help facilitate the improvement of that soil and basically to grow your way out of it. Okay. So the second thing that most people try to do is they try to leach the salts from the soil. And to do that, they use drainage pipes, they lower the water table and allow those salts to then move down through. Okay. Will the salts leach by themselves? Yeah, they will over time. If in fact that you have more precipitation than you do evapotranspiration. If you have more evapotranspiration than precipitation, it's not going to happen. Okay. So the groundwater, if you're going to leach them, you got to get that groundwater below the capillary fringe. And if you have high clay soils, man, that water can migrate up about 4 feet. So that means you have to get the tile drain down low enough to keep that water and the salts from wicking up into the rooting zone. So then the downward water has to have a place to go too. So the best case scenarios, slow and steady rainfall, melting snow. You can't make more water, but you can concentrate it. So one of the things that, snow management is a tool to manage salinity, right? If you can concentrate the water, because think about this. Here, you only have about 1 inch of snow to melt down and infiltrate. Here you have about 3 feet. Well, which is going to move more salts? 3 feet of water. Okay, so if you can concentrate it, then you can start to move those salts. Okay, so the differences between saline and sodic. Salts tend to help flocculate the soils. They don't normally hard set. Water moves similarly compared to normal soils, because there's really not anything negative to do with the soil structure per se. But the plants will be more negatively impacted, of course. Sodium tends to swell or disperse soils. Soils can become hard set, really hard. Water movement can be basically down to 0. And we'll show that in the next video. can impact plants, but basically causes this really restrictive root layer. So here's an example of what flocculation and water movement. So if you have good structure, water will move through just fine. If in fact you start to get swelling, the water will tend to sit and pond. And then you get to the worst case scenario, and this is a complete breakdown of the aggregates, and we'll show a short video of this. So here on the x-axis, we have electrical conductivity, a high range of 0 to 14. And here we have basically field capacity water. So if you saturated a soil and you let the last drop drip out, that's how much water the soil can hold. But here, if you have soil with a high SAR, that means a high amount of sodium compared to calcium and magnesium. If you have 0 electrical conductivity, you're almost at 32, and the reference line is about 18. So look at that, that's basically swelling. That's how much water the soil imbibes over its field capacity. So as you start to increase the electrical conductivity, you start to get to something more normal. Okay, so there's 2 main reasons why this occurs for the dispersion. Sodium concentrations are elevated and the salinity is low. So here's a video showing a time lapse of what the dispersion looks like, and you'll have to picture this in the video that Dr. Arnall will show next. Here, after 10 minutes, this is a ring of dispersion that will occur. This soil had a high concentration of calcium and therefore did not disperse. So to control it, one often adds a salt like gypsum. So what the gypsum does is it adds calcium to the soil solution, but it also adds enough electrical conductivity to keep things flocculated. Here, the same soil was in water. And notice you can see that halo of dispersion around there. So to help control sodic properties, you have to get the electrical conductivity elevated. And to do that, again, we oftentimes will add gypsum. So here's an example: high sodium system, low electrical conductivity. If you add calcium amendments, you'll start to get water to move down through. Okay, so keep in mind, not just knowing the level of sodium, calcium, magnesium, or potassium is the whole story. The level of soluble salts greatly controls the swelling and dispersion. Okay, so this is an app that we had developed. It's the only gypsum requirement determination app out there, surprisingly, you know. But if you want to download it, just go to your app store or whatever and just type that in. You should be able to download it pretty easy, and it's based on equations by Jim Oster, who is also from North Dakota but spent his career in Riverside. Okay, so recommendations. So we went through a very quick overview, but overall, saline soils. So a soil sample to monitor changes over time. You may need to use salt-tolerant crops in certain areas of the field. Choosing the correct plant for the soil condition, instead of forcing a crop to grow in an area where it's going to struggle. Leaching lots of water is essential. And that's one of the that's the hard thing to do, right? When you don't have excess water. Tile drainage will eventually help, but it takes time. Sodic soils, soil sampling is the only real way to determine the levels of sodium and electrical conductivity. If you're going to put tile in areas that are suspected to be sodic, core down to 4 feet and sample every 1 foot. Break it up into 1 foot. And then, so you can determine if there's any sodic layers in the soil profile. Gypsum or other calcium amendment will be quite helpful to help move that sodium and elevate the electrical conductivity. Okay, so Dr. Arnall is going to show you a video next. So that this is, fortunately, Bernie, one of my students, made this for me. So, but I don't think Bernie is going to show up today, but we'll see. So, okay. Brian, I'll put it back to you.